Example 3 looks much harder than it is. We have a block up at the top of this ramp. It slides down the ramp. It slides over a rough patch. It runs into a spring. It compresses the spring and comes to rest. So from the beginning, we're turning gravitational potential into kinetic down here. Then we're going to take some of that kinetic and turn it into heat and internal energy. Then we're going to hit the spring and turn the rest of the kinetic into elastic potential. The thing is, you don't have to actually solve for all of those parts. We start off with some gravitational potential. We end up with some elastic potential. We're not concerned with what the kinetic energy was in between. The difference between the gravitational potential we started with and the elastic potential we end with is what we lose to internal. So if we look at our initial gravitational potential, that's just mgh, the height of the block multiplied by its weight. And if we plug in some values for that, I got 117.6 joules. Now at the end, we're going to end up with a compressed spring. So the final potential energy we're going to have is 1/2 kx squared. All of those values are given. I plug those in, I got 71.875 joules. That makes for a net loss of 45.7 joules. So that 45.7 joules has to equal the magnitude of the work done by friction, which is going to be equal to our change in internal energy. Well, the work done by friction is the coefficient multiplied by the normal force, which in this case is mg because it's flat, multiplied by the distance that it travels. Again, all of those are given, so you can rearrange this, solve for our coefficient, and I get 0.194. And remember, coefficients of friction are unitless, so that is the final answer.